I want to do this example because this example is very similar to what you're going to run into in 5, 6, 7, and 8 on the other side. Okay, 50-kilogram person's climbing down a rope. They're accelerating downward at a rate of 1.5 meters per second squared. What do I need to do first? I've told you there are 3 steps to solving these. What's the first step? Before that. But you're right, that's the second step. That's the first part of the second step. That's step 2A. What's the first thing? Draw a picture. Draw a picture showing all the forces acting on the thing. So do you think the thing here is the person or the rope? It's the person. And I don't know how you figure out what the thing is, except you're being asked about the person's weight. And I don't know, the tension in the rope. I don't know, yeah. So it's the person. If you need to ask me, what's the thing in this problem? At least in the beginning of the year, I'll tell you. So the thing is the person. I want to show all the forces acting on the person in my diagram. There's the rope, there's the person, they're climbing up. I'm going to just put in the acceleration. I'm going to write it up here. Acceleration is, and I'm also going to show it in the diagram. Acceleration, 1.5 meters per second squared. Now I want to give direction to it. Which way is the acceleration? Down. So they're either climbing down, or they're sliding down, or somebody's lowering the rope down while they're holding on. We don't know. It could be any of those, but this person's accelerating downward. Now if I just write it numerically, it's going to be how many meters per second squared? Negative 1.5 meters per second squared. So when I do the math, that's what I'm going to use, but for my diagram, this. Okay, tell me a force acting on the person. Gravity. So which way? Down. And instead of, I'm not going to call it gravity, guess what I'm going to call it? Force of gravity acting on an object is? Weight. And I'm going to just write, I'm going to go ahead and write the weight formula, because I could either write weight here or I could write how you calculate it. What is the formula for weight? mg. And are there any other forces? Mass is just resistance to acceleration. It's not really a force. If you get massive enough, then you have a gravitational pull. But for people, that's going to be negligible here. So it wouldn't include mass. Just think about things that are pushing or pulling on this person. If weight were the only thing, what would the acceleration be? If this were the only force acting on the person, what would the acceleration be? What? 1.5. No. 9.8. 9.8 downward. They would be free falling downward. That's when only your weight is acting on you, you're in free fall. So they'd be accelerating downward at 9.8. So that tells us weight is not the only force. There's got to be another one. What's the other? If you imagine you're this person, you're just sensing any sort of pushes or pulls. What's pulling on you? Yeah, the rope. Which way is the rope pulling? Up. And the word that I use for the force of a rope pulling is tension, T. And those are really all the forces. For physics problems, unless I say otherwise, we're pretending there's no air. Because when you get into air resistance and drag, the drag equation is complicated, and we just don't do it on tests much. So there would be buoyancy. I'm not going to get into buoyancy. But so there's the tension pulling up, and there's the weight pulling down. Which one's stronger? Which one's winning? Yeah. This is, because they're accelerating downward. Okay, so there's my diagram. That's the first step. Second step is just what, I forget who it was said, but I want to write 2 equations for net force. And the one I always think is easiest is Newton's second law. F equals what? Ma. So the mass of this person times their acceleration is equal to the net force. The other way to get the net force is to do what? What? How do I get the net force? By the way, I could just plug these in now. I could plug in 50 times negative 1.5, and I could get the net force. But there's another way I can get net force. mg is part of it. I'll write mg over here. I'm going to put it right here. That's going to be part of what I'm writing. What else am I going to write there? So two ways to get net force. One is to use Newton's second law. The other is to add up all the forces. The net force is the vector sum of all the forces. So of these two forces, which one's negative? Weight, mg. So I'm going to put negative mg. And tension, is it positive or negative? Positive. So this is the net force. The net force is T minus mg. So the problem-solving strategy is to draw a picture, show all the forces acting on the object, in this case the person, and then write two equations for the net force acting on the object, the person. So net force equals ma, net force equals T minus mg, and then the final step is to do what? Set them equal and then solve. So I've got two different expressions for the same thing. ma equals T minus mg because they're both net force. I could plug in everything and then solve. I'm going to do it the way students generally don't like. I'm going to do it algebraically first because it's actually going to save me a little bit of calculation. So ma equals T minus mg. Are you seeing where this is going? So what I want to say, the reason homework is important is because right now I'm talking through this, you're trying to follow what I'm doing. It might make sense, but you don't have time to step back and see if you really get it and ask me good questions. There's just no time for you to process. When you're doing the homework and you try number 5 on the other side, or 6 or 7 or 8, that's when you can see if this stuff really stuck. And that's when you need to ask me about it if it didn't stick, so I can go back and clean up any remaining issues. So I'm just going to do some algebra, which is really a good idea. I want to simplify this. I'm going to add mg to both sides. So on the left side I have ma plus mg, and that equals t. And I'm going to do one other kind of neat little thing algebraically. Guess what I'm going to do to simplify this a little bit more? And maybe I'm using the wrong one. What? Yeah, so we've got m and m in here. I'm going to factor out an m. I'm not a math teacher, so I may use the wrong word sometimes, but m times a plus g equals t. I think that's simpler that way. The reason this is simpler is if you start plugging in masses, if we hadn't done that, we'd have 50 over here and we'd have 50 over there, and then we'd have negative 1.5 here, 9.8. So I've just saved myself one thing I have to put into the calculator. Instead of having to put in 50 twice, now I just have to put it in once. So there were two questions. I'm doing part B first. What's the tension in the rope? Now I'm going to plug stuff in. The person's mass is 50 kilograms, and the acceleration is negative 1.5 meters per second squared. What's g? What? 9.8, positive 9.8. G is always a positive number. 9.8 meters per second squared, and that equals t. So I'm just cheating and looking at my answer key. Can't find it in my answer key, so let me just do this. So this is kind of cool the way this formula works. You could use this for a lot of different situations, and I'll talk about those in a second. I wouldn't recommend it. I'd just derive it every time. But 9.8 minus 1.5 is 8.3. So 8.3 times 50 is 415. So T equals 415 newtons. That's the tension in the rope. Oh, 415 newtons. Now, before I even do the person's weight, do you think their weight is going to be heavier lighter or the same as the tension in the rope. So the person is hanging from the rope. They're accelerating downward, either because they're sliding down or because somebody's lowering them down, or they're just climbing down. So right now there's 415 newtons of tension in there. Do you think their weight is more than that or less than that?
More.
So a couple ways to do it. Weight is mg, and this is m times g, but it's not m times g, it's g minus a little bit. So this number right here is a little bit less than weight. If I want to do the exact weight, it's going to be 50 times 9.8, which is 490. So the person's weight in newtons is 490, and the tension in the rope is 415. So tell me if this makes sense. Here's the, I don't know, let's just say that's the hand of a giant holding this person up here. If you're holding this rope and you're letting this person slip downward and accelerate downward, is that going to, like, say you're holding them and then all of a sudden you start to let the rope slide. Does that make the rope tighter or less tight?
Less tight.
Less tight. And that's what's happening here. It's less than the weight. Now, if all of a sudden you yanked up on this rope and you started to lift the person, what would that do to the tension here? It would increase it. So just if you went through all these steps, and if we had, instead of a negative acceleration, if we had a positive acceleration, what we're doing here is just adjusting g by, in that case, if you yanked them up, that's like increasing g. That's like increasing the weight. And if you lower them down, that's like decreasing g, decreasing the weight. So you feel more tension when you pull something up. You feel less tension when you're letting it down. And when you just hold something, the tension equals the weight. All right.